For 2.1, you've been introduced to three models of electron. The first one is Bohr atomic model. So for Bohr's atomic model, electron is circulated to move around the nucleus at fixed distance. And then Bohr also unable to explain the dual nature of electron, and also unable to explain the extra lines formed in the emission or energy level diagrams. Okay, so for example, Bohr, you've got an electron at, let's say, n equal to 1. So this electron will circulate it around n equal to 1 only. And then comes de Broglie postulate. Okay. De Broglie said that electron can behave as wave-like and particle-like. This finding by de Broglie was further questioned by using Heisenberg's uncertainty principle. Okay, because Heisenberg said that it is impossible to know simultaneously both the position and momentum of an electron. This is because in de Broglie, de Broglie said that electron moves randomly. So instead of circulating around n equal to 1 only, this electron, this red electron, when excited or been given an energy, it can move directly to n equal to 3 or move to n equal to 2. Okay, so that's why Heisenberg said that it is possible to know both the position and momentum of an electron. So all these problems were later solved on by quantum mechanics or quantum mechanical model. So that's how we're gonna move on to 2.2. So for quantum mechanical model, okay, so there are 4 quantum number. Okay, the first one is principal quantum number or symbol n, which is your number of shell. Okay. So for n1, for n equal to 1, 2 electrons can be filled. For n equal to 2, only 8 electrons can be filled in, and the rest follow on. Okay, so second quantum number is azimuthal or angular momentum quantum number, or L, which is your shape of orbitals. So for n1, in order to find your L, your n, which is your number of shape, must be minus 1. So for when n equal to 1, your L must be 1 minus 1, which is 0. So when L 0, 0 is for S shape. So you've got 1 S. For n equal to 2, your L must be 2 minus 1, which is 1, and 0. So make a note that 0 is a must for L. So this is your maximum L value. Okay. Your minimum L would be 0. So for n equal to 3, okay, we want to find your maximum L, so that would be 3 minus 1, 2. 2 is your maximum L. So you should write 0 and 1 at the front. Okay, and that would stand for shell is 3. So you've got 3, 0, which is 3s, 3, 1, which is 3p, and 3, 2, which is 3d. So for F, that is when n equal to 4, so you need to find your maximum L first. So that would be 4 minus 1, 3. 3 is your maximum L. So your L would be 0, 1, 2, 3. Okay. So for 4, when n equal to 4 and L equal to 0, that would be 4s. When n equal to 4 and L equal to 1, there would be 4p. When n equal to 4 and L equal to 2, there would be 4d. And when n equal to 4 and L equal to 3, that would be 4f. Got it? The next thing is magnetic quantum number, which has a symbol of m. M is the orientation of orbitals. When n equal to 1, okay, I'll just copy down this n and L from azimuthal or angular momentum quantum number. When n equal to 1, L must be 0. Okay, so your M is just the plus minus of L values. So when L equal to 0, M must be 0. Okay, you don't have minus 0 or positive 0. No. So that's why for S orbital or for S shape, you've only got one at one orbital diagram. For n equal to 2, your L must be 0 and 1. So for 0, you've only got 0. For 1, you have negative 1 and positive 1. So in total, you've got 3m. Okay, so for 3m, you've got 1, 2, 3. So there must be 3 orbitals diagrams. When n equal to 3, okay, so you've got 0. 1, you've got negative 1, positive 1. And for 2, you've got negative 2 and positive 2. Okay, so I'm going to rearrange it to become this way. So negative 2, negative 1, 0, positive 1, positive 2. That would be in total 5 orbital diagrams. For n equal to 4, you've got L of 0, 1, 2, 3. Okay, so your orbital diagram should has 1, 2, 3, 4, 5, 6, 7 orbital diagrams. Okay, so make a note that the arrangement for m values is not fixed. Okay, so for example, when n equal to 2, L equal to 0 and 1. So this is how you're gonna write your orbital diagram. So M would be negative 1, 0 and positive 1, or it can be 0, negative 1 or positive 1 or positive 1, 0, negative 1. Okay, so the arrangement for M values is not fixed. Okay, so you can start with negative 1 first, or 0 or positive 1. And the last thing in quantum mechanical model would be the electron spin quantum number with the symbol of S, which represents the spin of electron. Okay, so for clockwise, it has a positive half. Okay, so why is it half? Because this is how you're gonna write electron in orbital diagram. Okay, so the arrow is half-headed. Okay, and the orientation is positive, so it should be upwards. Okay, so for when your electron is negative half, okay, so negative, then your arrow should point it downwards. Okay, so this is your positive half and this is your negative half electron spin quantum number.